You can start, Thomas.
Okay, good. Thank you very much. The recording has started. Thank you. Thank you for showing up. It has been a long week. It has been a long 3 weeks. So thank you for being there. Uh, so today I try to wrap up a few things that I really wanted to tell you. And then we see how long it goes. And from there, afterwards, we can have some kind of open discussion. Okay? Good. So, let me go right into it. What did we do yesterday? We were constructing some gentle algebras from marked surfaces. So this is the main topic for today, and yesterday already the relation between gentle algebras and marked surfaces. So what we did back in 2008 was with Ibrahim Assem and Ibrahim Gabriel and Pierre was that we have a marked surface and then we fix a triangulation. I will later talk about generalizations if you don't have an actual triangulation, if you have other ways to dissect your surface. But for now, I would like to explain everything in triangulations because you can see the most important parts, the most important properties are visible there, and it's kind of easier that setting. The proofs are clearer and so on. Yeah. So we have a triangulation of the surface, and then we construct an algebra, which I denote by A associated to the surface, to the triangulation, given by a quiver and relations. And the way this goes is that we construct the quiver and the ideal simultaneously. So when we have a triangle, then the arcs of the vertices of the quiver are the arcs of the triangulation, and whenever two arcs I and j are adjacent edges in one joint triangle, then we draw a clockwise arrow from the first to the second uh, point in the quiver. And whenever we have such an internal triangle made of three internal arcs, we demand that there are zero relations for all those three compositions. And other than that, there are no relations. Yeah. So this is how we construct an algebra for every triangulation of a surface. We have shown that this algebra is a gentle algebra, satisfying very nice relations. And those gentle algebras have already been around since then, since the 80s. And so the kind of gentle algebras you get in this way are algebras whose relations are all concentrated in such three cycles, because this is how we constructed them. And then this is connected in general by kind of by some paths or walks without any relation. So this is how they look like, really. Okay. And then I told you that you can do also you can define also a categorification of that situation. So when we have a marked surface uh, and we fix a triangulation, or actually we don't need the triangulation, the cluster category is independent of it. So just when we have a marked surface, we can associate a category to this, the cluster category, in such a way that we have bijections, the triangulations of the surface correspond to clusters in the cluster algebra, which is associated to the surface, and they correspond to cluster tilting sets in that cluster category, okay? And moreover, there's a very close relation between the cluster category and the category of modules over this gentle algebra, namely up to finitely many objects. Yeah, if I mod out this cluster tilting object, they all have the same number of objects and the number of arrows in the triangulation, number of arcs in the triangulation. When I factor out finitely many objects, then I really get an equivalence between the objects in the cluster category and those modules. Now, the good thing about that is it is a gentle algebra. So for gentle algebras, we do know all the modules based on the work of Butler and Ringe, also in the 80s, because they have shown that all the indecomposable modules here can be described, some combinatorics using strings and bands. Uh, so the question is, can I use that combinatorial description of strings and bands and interpret it on the other side in the uh, in say in the surface? Yeah, I mean those strings correspond to certain objects here. They correspond to certain objects in the surface. What is that? Yeah, and the answer to this question is we also gave in that paper that this time I have to fix a triangulation. And once a triangulation is fixed of the surface, then the following sets of objects correspond bijectively to each other. There's a bijection between the string modules in that gentle algebra. This is what you can control always for every string algebra or every gentle algebra. You can give yourself a set. You can describe indecomposable string modules. They are given by strings. Strings are walks in the quiver, which are reduced walks and which avoid the zero relations. So such walks in the quiver correspond bijectively to curves in the surface. Now I say curves, not arcs. So those things might have self-intersections. Yeah, this is a more general class. Like the strings, they can walk around the quiver several times and kind of intersect themselves. The same thing happens for the curves in the surface. Okay, so these objects correspond to each other bijectively. So we get kind of a geometric description, a geometric module of the string modules given by just by curves or walks in the surface. So this is a kind of a nice correspondence. Right? I find it nice because I like to draw pictures and diagrams and curves. Okay. Okay. And then we convinced ourselves that this is actually possible. And I would like to give you some examples on that. But before doing so, I gave you a little recall of what have we done, where are we at this moment? Do you have any questions at this point?
You said that we can choose what string modules we want in a. What did you mean by that? I couldn't understand.
Maybe that was wrong. I mean, the modules, all the indecomposable modules in this algebra are either string modules or band modules, and I wanted to focus for now only on the modules of the first type, only on the string modules. Yeah, there's a corresponding theorem for band modules. They would correspond to closed curves, but the string modules are just any curves in the surface. That's all what I wanted to say. Okay, good. Thank you. Um, okay, then let's go on. Let's move on and let's do a couple of examples. Let's do a couple of examples of how does a curve in the surface correspond to a string or a string module. So I start with some very innocent examples, and you can suggest me some if you wish. Let's say if I want to include the audience, I should label those marked points 1, 2, 3, 4, 5, 6. If you have any suggestion, can be also in the chat. Which curve you wish to consider, you can tell me. And you got your minute, and you didn't tell me, so I make my own choice. So I choose
Three
gamma.
six. Okay.
Sorry,
3 6. Like.
this was the exact same that I wanted to do. Okay, good, thank you. So I take this curve from 3 to 6, this one. Okay, good. So that's my curve gamma. And what is the corresponding string? So as I walk along the quiver is inscribed here. as between the arcs of the triangulation. So I start with gamma, I hit 3, then I continue to 2, and then I end up in a mark point. So what I see is only this one arrow between 3 and 2. This is the only part that the string sees. Sorry. So this is my string that corresponds. This is the string W of gamma that corresponds to this curve. That's okay. And then the string module M of W gamma is the module which is one-dimensional in 3 and in 2. And the identity here, and it is zero-dimensional at the vertex 1. If I orient my quiver, sorry, I have the backward orientation. If I orient my quiver like a 1, 2, 3. Okay, so this is good. This works fine. Are we okay? Let's move this out of the way. And good. So this is fine. If what is the simple module in 1? This is corresponds to gamma, which crosses just the arc labeled number 1. So that would be the string 1, the module would be the simple in 1. And we find all the simple modules if we cut just only 3 or only 2 or only 1. These are the simple modules, and in general you find arbitrary modules. So this one would be the largest module. It is goes from 3 to 2 to 1. This is the module KKK. That's good. In that result, I say the curves which are not part of gamma, yeah. I mean, what happens if I choose a curve which belongs to gamma? If I choose a curve which belongs to gamma, for, say this one is my gamma, then to some degree that curve doesn't really intersect transversely, diagonally any of the arcs. I mean, it's equal to one of the arcs, but the thing that I want to see is in general, I start with a curve gamma at some mark point. I move along in some triangle, and then the first time I hit one of the arcs, I notice its label. Yeah, so I start from here, but the curve gamma here never leaves any triangle. So this curve gamma here doesn't correspond to any module. Yeah. So we do have the indecomposable modules, all indecomposable modules, and then plus we have one copy of an object in the cluster category that for each arc in gamma in the triangulation, we have one copy of one object in the cluster category. And that corresponds to what we already know, that the cluster category is given by n copies of some strange objects that are kind of shift 1 plus the module. So this is what you get, okay? Okay, fine. If we have that quiver, then curves would be like gamma. The curve gamma would be like this. The string would be, I go from 1 to 2, and the corresponding module is the module K0. And if I consider my strings, that's what we discussed yesterday already. Strings are supposed to have minimal intersection number with the given arcs. So I cannot consider a string that would I don't know, that would go intersect these two and then go back there. This is not the copy of the string that I allow. I allow only as straight lines as possible going between the endpoints. Okay, that's good. Okay, so if we have, for instance, such a triangulation, this one here, if I would consider that one, just to illustrate once, I could here take a curve gamma that would head off in the direction of one of the triangles. So I go there, then I move along in the triangle for some while until I cross one of the arcs. So at this moment, if that one is gamma, at this moment the string associated to gamma would say, okay, I hit one arc, so I would note that I cross two, then I go over to the arc one using that arrow here. So this is the arrow alpha and the arrow beta. So with the arrow alpha, I would go here. Then I follow my string along. Nothing is happening. I stay inside until I hit again two. Uh, if I hit again two, then I was moving along beta. So I was moving, but uh, sorry, alpha has the other orientation, you know. I mean, if I come from here, then I follow alpha in the reversed order. You can tell me when I make a mistake. So that should be like this, okay? And moving along from here along the arrow beta means I continue like this beta until I come back to two again. So I'm at this moment I'm at that point, and I can, if you wish, I can continue moving to one, and then let's say we finish at some point. So I want to finish and end up here. Good. So that's it. So you can see that the curves, they can have self-intersections. These are not arcs anymore. And self-intersections means that I repeat coming along across the same arc several times. So this is totally allowed. This is fine in general, yeah? As long as those curves are still have the minimal number of intersections with the given arcs. This is a very valid choice. And such okay, and such strings allow us to build up more complicated modules. So this would be kind of the module K, 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 K. But I have to view this module on the quiver, and the quiver is that one, right? So over that quiver. So what module would this be really? That would be the module. Okay, I have two copies of one. I have two copies of two, and under the map alpha, so there's alpha beta, and under the map alpha, the first copy goes to the first copy. Under the map alpha, the first copy goes to the first copy. And this one again is the map alpha, so I have identity map here. And under the map beta, I would see that the first copy goes to the second instance here. So maybe the matrix corresponding to beta would be this one. Yeah. So like that, you can build up representations. I hope I made no mistake. That's good.
Um, I wanted to ask that do we also count like the arcs which we are following along our curve, uh,
Yeah.
and not just the
Yeah. 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 Yeah.
intersection?
Yeah, yeah. So I'm coming along with my curve here. So I hit alpha the first time. I hit the number two, and then I go from here to from two, I go to one, and I go along the arrow alpha. So I need to record this. Yeah.
But so like in the above example, the one where we had A3, uh,
Mm-hmm.
the one we didn't count the
Yeah,
arc three. The, uh,
yeah. I mean, there's only a unique arc between any two vertices, so I didn't write them down.
so like not this one, the third example in this line.
This one here.
Uh,
This one?
yes.
Yeah, but this is a non-example because this is just to illustrate this gamma was a part of the triangulation, and then I don't do anything. This corresponds to nothing.
But here also it goes along the arc. No?
Yeah. So the real procedure is really that the curve gamma starts in a marked point, then it enters a triangle, and the moment it leaves this triangle by hitting an arc of the triangulation, then I write 1. This was the index. This one here kind of never enters, oh, sorry, this one never enters and never leaves any triangle, so that doesn't correspond to any module. This
Yes,
is the
thank you.
convention. Okay, good. Okay, good. So these are my examples. Now you can understand the indecomposable modules uh, of this uh, cluster algebra, of this gentle algebra. You can understand the indecomposable modules by certain walks, by certain curves in the surface. Uh, they also correspond to objects in the cluster category if you wish, but maybe we can forget the cluster category. We just want to interpret modules over gentle algebras geometrically as curves in the surface. And what else has been done for curves in this for gentle algebras or for string algebras? We do know, thanks to the work of Butler and Ringel. Oh, okay, sorry, I was skipping that. Okay, doing this with Chang Che, my student Chang Che, we just note that we get a full description of the cluster category by string objects and band objects. Okay, this is you have seen this already. Okay, uh, what I really wanted to discuss is the irreducible morphism. So this is something that we really need to take to pay attention a little bit once more, even if it's Saturday and the last day. Uh, So Butler Ringel in their paper, mostly the new thing which they gave us was a description of the Ausländerreiten quiver. Uh, the description of the modules of the indecomposables was based on previous work from Russian mathematicians. There, really, the new contribution was the Ausländerreiten quiver, I would say. Yeah, and they have a combinatorial recipe to construct the Ausländerreiten quiver to. Do you know this? To which extent, Amit, did you discuss that?
I mean, I briefly discussed that, but I don't think they will remember.
Let's do it anyways.
Yeah.
That's good. Okay, perfect. Um, so there's a combinatorial recipe, there's a description. So suppose we have a string object. We have a string algebra. Suppose we have a string. We have a string in that algebra, call it W. Okay. From that string W, I want to construct a few other things. Uh, One is called WH, to the H is to the left. This is obtained as follows. We take W, then we extend it on the left by an incoming arrow, and then we go down as long as possible until we reach a sink in the quiver. So such a shape they call a hook, and this is a hook extension from the left. Yeah. Uh, of course, one could also consider hook extensions from the right. This string would be denoted W hook on the right, okay? And then we have also the string where we extend hooks on the left and on the right. So that would be this one, yeah? Um, if all those hook extensions left and right do exist, this is not guaranteed, but suppose they exist for the given string W, then Butler and Ringel showed there's an Ausländerreiten sequence that starts in the string module at W, whose middle term is the direct sum of these two hook extensions left and right, and whose end term is this larger module where we extend W by a hook left and right. Okay, there's an Ausländerreiten sequence. Ausländerreiten sequence in particular means there are irreducible morphisms from MW to extend by a hook and to extend by a hook on the other side. Yeah, these are irreducible maps. And all Ausländerreiten sequences, so first they show this is an Ausländerreiten sequence, and secondly, they show that all Ausländerreiten sequences are obtained in this way or similarly by some other recipe. Uh, I I avoid some details here. I mean, sometimes you cannot add a hook because there's simply no such arrow in the quiver. But you could also consider a dual concept where you delete such a thing from your given string W, and then there's a mixture of maybe 8 cases or so. So either you can add a hook on the left or on the right, or you delete such a core hook on the left or on the right. And so there's a couple of cases you need to consider. But there's a really combinatorial recipe that describes you all irreducible maps between uh, string modules. That's very nice. That's what we have. Okay, good. This was a quick summary, Amit. This is fair enough.
Yeah, sure. I also told it in similar way that
Yeah.
check a inverse syllable and direct syllable. Yeah, that's
and and then of course we have our description of the cluster categories given by in the composables who are either string objects or band objects. So let's focus on the string objects. They correspond to curves. So suppose this is a curve and we ask ourselves the question, there's an irreducible map from this curve to that curve. What does it amount to in the surface? What is the operation? Okay. Good. So we look at that with Changqi in 2010. We basically translate that nice recipe into the geometry of the surface. Good. And here's the answer. Um, here's the answer. Can you see this? Okay, so here's the answer. Consider a curve gamma in the marked surface. It's actually, yeah, okay. Consider a curve gamma in the surface, and the curve starts somewhere in a point M1 and it ends somewhere in a point N1. And then I want to change that curve slightly. So if I denote by M2 and N2 the clockwise successors that are marked points, yeah, then I can define 3 other curves. Yeah, so let me do this. So if I have the curve gamma starting here, then I walk over along the boundary to the next marked curve, to the next marked point, and then I can construct the curve gamma, and I shift it. Uh, I shift it down on the left hand side. So I look at that curve gamma S here, or I could look at the curve gamma and I extend it on the other endpoints, then this would be giving me this curve, yeah. And if I take gamma and I move it both left and right, then I would get a curve which is homotropic to this one. Sorry, this one. Okay. So I do get 4 curves: gamma, gamma E, gamma S, and gamma SE. And then there's an Ausländerreiten sequence in the module category of I gamma, which is of the form gamma, uh, and there's an irreducible map from gamma into gamma S and gamma E, and these form the middle term of a sequence that has gamma and gamma S E as its end terms. Okay, good. So it's a kind of a nice description. You don't add hooks or you add co-hooks or do stuff like that. I mean, you simply take the curve that you are given. Sorry, what did I do? You simply take the curve gamma that you are given and you slide it along to the next marked point on the surface. And by homotopy, you can say, this is my new curve. So these are 1, 2, 3 curves you can construct like this. And they are the immediate in the immediate neighborhood in the Ausländerreiten quiver, meaning there's an irreducible morphism from gamma to gamma S and from gamma to gamma E, and both of them map then into gamma SE. That's the description, okay? Good. Proof. Where does this come from? Can we understand this? Are you ready for it? Let's prove this. Let's try to prove it. Are you okay? Okay. Let's try if we can manage to understand. So suppose I'm given my curve gamma, and I want to compare it to this curve gamma S. The difference of these two curves is only on one end where I move from one marked point to the next one. So if I focus on that end, they have the same endpoint. The curves gamma and gamma S are the two I'm focusing on, and they share the same endpoint. So they will enter in a triangle, in the same triangle together. So they both enter the same triangle here simultaneously. And they will simultaneously hit or intersect with the first arc in the triangulation gamma. So they meet, they intersect at the same arc gamma. And this will go on for a little while. So for some little while, they move parallel through all the triangles. And up to here, I cannot distinguish in the string combinatorics, I cannot distinguish between gamma and gamma S. Yeah. In the string combinatorics, they hit the same arc in the triangulation, they hit the same arc in the triangulation, they hit the same arc in the triangulation. Up to here, these two curves are totally identical. They are homotopic, okay? But, I mean, they are different. Gamma ends here and S gamma ends here. So at some point, we have to hit a triangle where they don't go parallel, yeah? And this can happen if gamma ends right here. Gamma ends right here, meaning from that triangle, the last triangle where they were parallel, gamma goes to the marked point. It doesn't intersect any arcs anymore. Gamma ends here, okay? So if gamma ends here, what's the possibility for S gamma? S gamma still needs to go on to meet this point. Yeah, so S gamma, but if gamma ends here means I close a triangle, so there must be one triangle. There must be one triangle that gamma goes to one of the endpoints, but S gamma does not go to this endpoint. Therefore, S gamma must continue here, and it must intersect with that arc of that triangle. You see what I do? If it intersects with that arc of that triangle, we go clockwise. So it goes against the direction of this arrow here. The path, if I follow it here, it goes against the direction of that arrow here. And then I might still not be at the marked point, so maybe I still have to continue. But the only way to continue is like a fan of those triangles that will be intersected in that way until eventually I go to the next mark point. Okay. Because there are no other triangles between these two. There's no marked point. I cannot have other triangles. The only way of triangles building up between these two neighboring endpoints is there's kind of fan of such triangles going out in one direction. Okay, so if I look at what's the difference between gamma and S gamma, gamma ends here and S gamma goes against the arrow, and then it goes with the arrow until it ends. And this is exactly the shape that we had produced here. I mean, there's a string that ends here, or there's a string that continues. It goes against one arrow and then it goes down as long as possible until it ends there. So the difference between W and that other curve, so this was gamma and this was gamma S. The difference between these two is I add a hook. Yeah. And then Butler and Ringel tell me, yeah, then you have an irreducible morphism. Yeah. So this adding hook combinatorics translates in this surface nicely to I move the endpoint to the next marked endpoint. That's all what it is. Yeah. And I was sweeping some cases under the rug. I mean, maybe it's not exactly like that. And then you have to look into the other possibilities, deleter, co-hook, and so on and so on. Yeah, but basically it's the same combinatorics that Butler and Ringel described here makes you that the irreducible morphisms, the Ausländerreiten translate of gamma is obtained by moving both endpoints clockwise uh, to their successor. This is the Ausländerreiten translate in that geometric model. That's good?
I have a question. So,
Yes.
how do you know that there is always another point? Like, if there is no other mark point, do you come back to the same one? And
Yeah,
what is
yeah,
and under
yeah.
what situations like you don't have such a possibility of hook?
Uh, I mean, there's the the mark point belong to the boundary, and
Mm-hmm,
on the boundary I go in clockwise direction until I hit the next mark point. If that boundary happens to have only this one point,
mm-hmm.
and my curve gamma was ending here, then the curve gamma s would be the one like so.
Okay,
Yeah, I mean, I really go along gamma and then I go along the boundary until I find the next mark point, even if it's the same. I mean, look,
right.
that's the same recipe. So it might look like this. Yes.
And what is the corresponding thing for gamma is not existing?
The
So this hook might not exist, right?
this hook might not exist. This hook might not exist. The hook might not exist. Yes, yes, yes. I would need to look in our paper. So locally in that situation, what did we say? Gamma ends here because gamma goes here to the endpoint. I mean, this is the last triangle that gamma hits. Um, it might be okay. Let me improvise. I don't know. What if we have our boundary component? This is M1, where gamma ends, and we say gamma S always ends here. Yeah. What could happen? What could happen is that the triangulation locally doesn't look like this, where there's a couple of triangles starting here. It could look like that. Uh, there's a couple of triangles starting there, right? I mean, at every I here that was kind of the
The
special case
point
where
along the clockwise the point along the clockwise boundary lies in the same triangle where
yeah, yeah,
gamma
yeah.
enters at the
Yeah,
end.
yeah. I
Yeah,
mean, this is a boundary arc, and this belongs to some triangle. There's one triangle. The only
yeah,
difference is that one triangle, it might go down or it might go up.
yeah.
These are the two cases. You see what I mean? Yeah. If I'm in the second case and that triangle kind of goes up, then uh, gamma S would be not intersecting those guys. It would end right here because from here it connects to the marked point on the boundary. So gamma S ends here, right? There. Sorry. This is the last point that gamma S sees, but gamma would continue a little bit, yeah? So gamma would continue here and then there and there and there until it ends. So in this case, gamma would be longer than gamma S. And what's the difference between gamma and gamma S? Yeah, there's a kind of a co-hook where gamma is longer than gamma S. So this is the second part of the combinatorics this is this part of the combinatorics, yeah? These are the two possibilities. Are you more convinced now? I mean,
Yeah.
I don't give you full proof, but I mean, kind of these are the two things that can happen. Okay. Uh, so listen, what I wanted to do now is I have no more preparations. I wanted to draw some diagrams for you. If you allow me to do so, some overview, what do we have? Since Amit was a bit asking about the history of this geometric realizations. Okay, I tried to produce a large diagram. There are string algebras, and inside the class of string algebras is a special class, the gentle algebras. And inside the class of gentle algebras, we have these gentle algebras which come from a triangulation. Gentle algebra of the form A of gamma, where gamma is a triangulation. This is the one that we considered. And you have the gentle algebra of type A, N, which is also a gentle algebra after all, right? So, and I want to give you some results that had been obtained. First, let's say the indecomposable modules. The indecomposable modules. I'm running out of space. I need one more. I need one more column. That's not good. Sorry, give me some. Let me downsize this a little bit. Okay, good. And okay, the indecomposable modules, I can try to classify them here or here or there or there. Okay, the indecomposables for a quiver of type AN, they are known, they are folklore, I don't know, they are known since the 1950s or so. They are in papers by Abiasis, Belfra. They are well known. And let me jump from here all the way to the other side, to the string algebras. Indecomposable modules over string algebras have been classified. The precursory work is really Gelfand and Ponomaryov in 1968. And then by Butler-Ringel in 1987. That was then well established in our community. So we know the indecomposable modules over string algebras. What about irreducible morphisms between those? So let's go for irreducible morphisms. They are also occurred in the same work for AN, and the irreducible morphisms have been shown between string algebras, have been described in that work of Butler-Ringel that we were just discussing. So this is all good. By the way, if you want to know all morphisms, there's still some way to go. If we want to describe all the morphisms in a string algebra, this goes some way further. So that was maybe Bill Crowley-Boovey. and Jan Schröer a bit later, that was 1999. Henning Krause was also publishing. Do you have some more references
Yes.
for this?
Yeah, Krause. Krause
I
for
add
band mass between band modules and string modules.
Krause. Okay, so around 2000, uh, all the morphisms were described for string modules. For all between all morphisms in the category of modules over a string algebra were described. Okay, that's good. Let's go into geometric models for the module category. So let's say geometric model for the category of modules. In case AN, this has long been described by arcs in a polygon, by diagonals in a polygon. This has long been known, so that has been observed by Schiffler in 2006 in terms of the cluster category, but that kind of has been known. You can model type A combinatorics by polygons. And to some degree, this goes back to Ptolemy 2000 years ago. Yeah. And then can we generalize to other types? Can we move on from the polygon to more general surfaces? Okay, yes. So this is what I had discussed. So in the paper with Assem, Gabriel, and Pierre Guy in 2008, we gave such a geometric model for the objects in the module, for the modules, given by curves and band objects. And Daniel Labadini Fragoso also worked on that triangulation case. For gentle algebras in general, that has been described by Karin Bauer and Raquel Coelho Simoes in 2018. So they extended the module, the model, the geometric description for modules. They extended it from triangulation to general surfaces. From what shall I say? They extended this model from that particular class of gentle algebras to the class of all gentle algebras. In fact, they did it for all string algebras later on. So there's Bauer, Coelho, Simoes, who have then results about the module category for any string algebras in 2024, as far as I know. So they moved on to generalize from our particular class of gentle algebras, which are given by a triangulation, to general gentle algebras and then general string algebras. They always have a geometric model for representations. Okay? And if we ask about irreducible morphisms, again, irreducible morphisms, that's what I just discussed. For irreducible morphisms, we have a geometric interpretation in our paper with Chang in 2010, and that has been extended to all gentle algebras also by the same authors a couple of years later. So that all works fine. Okay. And Schiffler has observed this in 2006. It works for AN-type algebras already. Now we want to, so everything about the module category has been done. You see, this is fully filled out, my diagram. That's okay? Do you have any, okay, good. Now let's move on from let's move on from the module category to the bounded derived category. So before I discuss geometric models, we should first talk about the indecomposable modules, the indecomposable objects. So let's first start with indecomposable objects in the bounded derived category of the algebra. This has been done for type A by Happel in the 80s. This has been done for general algebras to some degree by Assem and Skowronski. In 1987, but explicitly by Beckert and Merklen in a paper 2003. Yeah, so Beckert and Merklen give a description of the indecomposables in the derived category of a general algebra using what they called homotopy strings. Okay. Let me continue on this. What about, so we did not look into the derived category. We were really focused on modules. And what about the general situation of a string algebra? There is no such description. This is in general wild. There's no such description. This is a wild category, and we have no good description of the indecomposable objects. Okay, so the indecomposable objects have been described. The morphisms between indecomposable objects have been described. In DPA, they have been described by in a paper by Kanakci, Parkstello and Schroll in 2016. And then, so finally, we know the indecomposable objects, we know the morphisms. Finally, do we have a geometric model for all this? So the geometric model has been given by a number of people. So there's one geometric model for the derived category given by Haydn, Katsakov, and Kontsevich in 2017. There's another geometric model for the objects in the derived category of a general algebra by Lekili and Polishchuk in 2018. And there's a geometric model by Opper, Plamondon, and Schroll in 2018. So in 2018. So they came up all about the same time. There were a bunch of geometric realizations of the category of the bounded derived category of a general algebra coming up. Yeah. So if you ask me, Amit, what's the use of those geometric models? They will tell you, yeah, we can determine certain things that we did not see, that we see only in the geometry, and that we did not see before. Yeah, so they would argue that you can, for instance, determine when two general algebras are derived equivalent by determining are the two surfaces homeomorphic, and is some line field transported to some other line field, etc., etc. Yeah, but since it is a correspondence, of course, anything you can do here, you can do there as well, and sometimes depending on your taste, sometimes you find the geometric side easier or nicer, and sometimes you find the algebraic side easier or nicer. I mean, this is a they're equivalent, you know. So I cannot really tell you this is better than the other. It really depends on your taste, I would say. Yeah. What I what what's the really exciting news is maybe that these people come from a totally different area. I mean, they work in symplectic geometry. And they construct something called the Fukaya category, uh, and consider questions from physics like mirror symmetry. So this opens some connections to other areas of mathematics, and I think this is good. I mean, there you can talk to the people who do that, and maybe we can learn from them, and so this is beneficial. I think the geometric model is beneficial in this sense that we kind of find a connection to some different community in math doing different things. Yeah, and when they say a Fukaya category, this is a complicated object, but they would consider in the surface case the Lagrangians. This means subvarieties of half the dimension. But if the surface has dimension 2, half the dimension is something of dimension 1. These are curves. So what they consider are curves in a surface. Yeah, I mean, their Fukaya category has as objects the Lagrangians, so meaning the curves in the surface. And then we can say, yeah, I mean, we also consider curves in the surface, and we have some combinatorics, and this is governed by gentle algebras. So they learn something new, gentle algebras, and we maybe learn something new from them. So this is, to me, the most exciting part of the story, that there's new connections to new things, okay? So this is my table. Do you have any comments? Shall I add somebody to this table at that point? I'm sure I forget certain things. And everything can be extended to punctured surfaces and so on and so on. I didn't do that, yeah. That's okay. Okay, for now, is this a good overview over the history of geometric realizations? That's good enough. Okay, good. I have like half an hour. So in the remaining half an hour, I would like to just comment a little bit on those and these models. How far do they generalize what we have discussed so far? What we have discussed so far is that case. So when we don't have a triangulation, how do I generalize to an arbitrary situation? How can I model gentle algebras in general? And what does change? And the thing is, most things work in pretty much the same way as they were working for the triangulated case. That's basically the message. Yeah. So we can. This is the first point that I want to make. So we can go from here to here. This is point number 1. I can go from that particular gentle algebras to arbitrary gentle algebras if I allow myself to move away from triangulation by something called, so here I need to generalize. If I want to go from the situation we consider triangulation to the arbitrary gentle algebra, I need to generalize triangulation to something called a dissection. So the triangulation gamma, I generalized this one to a so-called dissection P. And the dissection P is still made of arcs in the surface, and it cuts the surface, this time not into triangles, but into general polygons. And those polygons can be of two sorts. Either this is a polygon that has exactly one boundary component, or it is a polygon that has got no boundary component at all. Yeah. So these are the two cases that you allow. You cut your surface into polygons instead of triangles, and then you have a dissection. And then you want to associate to this a quiver. I want to associate to this some algebra A of P. So a quiver plus relations. And you do this pretty much in the same way as we did it for the triangle. So, I mean, the quiver is given whenever I have two arcs in my dissection P, and I is a predecessor of J with respect to clockwise orientation at the joint vertex, then I would draw an arc in the an arrow in the quiver. So in the quiver, I would draw an arrow from I to J. And here it's not important if I have a triangle or if I have some larger polygon, I do the same thing. And the relation is also the same thing whenever I do have in my, maybe it's not a triangle, maybe it is a larger polygon, but whenever I have some consecutive arrows inside one polygon, I request that the product of these vanishes. So this generalizes really straightforward from triangles to polygons. And then the theorem is by Bauer and Coelho-Simoes that we do get all gentle algebras this way. So this is very good. So this time you can describe, you get a geometric model for any gentle algebra. This is very good. So that's the 2018 result, I think. Yeah. Okay, and then on the left-hand side here, we said that string modules for triangulation, they correspond to curves in the surface. What about this situation? Is there a nice bijection between curves and strings in that gentle algebra? Well, the thing is, this time there's a little bit of a problem. So this time when we have a larger polygon, like so, and we have a curve passing through the curves we always had in red, was it? We had a curve gamma passing through that polygon. Then we got a little bit of a problem. The problem being that if we go into our quiver, so it would pass that arc here. It would pass that arc, then we go along this arc, then we go along that arc. So there would be an arrow here, there would be an arrow here, but we said these are two arrows in the same polygon, there's a zero relation. So we would have a curve that passes through a zero relation. This is not what we want, yeah? So the curves do not correspond bijectively to strings in this gentle algebra. You see what I mean? And that means that we do not have such a nice bijection between curves and strings. And so they do consider certain permissible curves. Yeah, so they come up with the notion of permissible curves. So this one is not good. This is not permissible. And you need to adjust your set of curves that you consider by kind of requesting that the curve does not pass through a zero relation. Yeah. But then you really do the combinatorics of strings in your given algebra. I mean, this is a string, is a walk that does not pass through a zero relation, and you kind of consider those curves that do not pass through zero relations. So honestly, here I don't really see the benefit of the geometric model. I mean, you kind of you do what you know from string algebras. Yeah. And the strings do not correspond to all curves in the surface, because now all curves would go along zero relations. So you restrict yourself to the set of permissible curves. These are the ones which do not pass through zero relations. So that's basically what I wanted to say about this story, the model for the geometric model for gentle algebras. Okay. And I want to say some more words on this model. Before we go on from here to here, do you have some questions about this one? This was very quick, I know.
I have a question. So, like, if we want to find out a geometric model for a new algebra, so is it necessary to know the indecomposable objects first?
That's a good question. In all those cases, the guiding principle was that we do have a nice description of the indecomposables by certain strings, by certain walks in the quiver, and then we would just model those walks in something geometrically that corresponds to the quiver. Yeah, that was the guiding principle behind all of this. So if I don't know the models, the modules, I would not expect you find some nice description, some geometric description to start with. Yes.
Okay,
So
thank you.
that's what I try to say before. Okay, that's what I try to list in my diagram. So before we have always a nice description of the objects, the modules, and then you just try to translate that into a geometric model. Look, that's how it works. Okay. And it happened in the same way for the derived category. There was a nice description using some homotopy strings. The homotopy strings are certain walks in the quiver. And then you translate this into a model using some geometry of some surface. Works the same way. Yeah. So if you allow me, uh, if you allow me to go into this part here, like that one. This is building on that combinatorics of homotopy strings. Yeah. So if I would be interested in creating a geometric model for uh, the bounded derived category of a gentle algebra, for the objects, this is really um, given by Beckert and Merklen's description of homotopy strings. So maybe we start earlier. What is the geometric model for the derived category? What is the geometric model for the gentle algebra to start with? Let's maybe start with Sibylle Schroll. She was studying Brauer graph algebras, and the geometric model for the algebra itself is the ribbon graph, also called the fat graph of the algebra. And that is really that you replace your arrows by little bands. Yeah, so like a sheet of paper, and you glue them together accordingly how they matched at arrows. And gluing sheets of paper together, you create a surface. So that is kind of given. Yeah, when you can view any algebra as a ribbon graph, and no, it's not any, but in particular case for gentle algebra, there's a nice way to glue them together. In general, you cannot glue them together to get an oriented surface. Yeah, but in case you start with a gentle algebra, Schroll showed gluing those sheets together, you do get a nice surface. And there's a bijection between those geometric models, those surfaces, the ribbon graph and the gentle algebra. So this is where she came from. And then once you have that geometry, and you have the Beckert-Merklen model of homotopy strings, which are certain walks in the graph, in the quiver of the algebra, then you just interpret these walks as curves in that surface, as curves in that ribbon graph, and you have your model that you would get a description of all the objects. So that's basically what they obtained. So they have this gives a model for this gives a model for the bounded derived category of a gentle algebra. Example, the algebra 1, 2, 3, 4 would correspond in their model to the surface which has like so 1, 2, 3, 4. So that goes 1, 2, 3. Oh, I'm missing 1, 4. Oh, no, that's good. 1, 2, 3, 4. Okay, so they create such a model where strings correspond to fans, and what would be the model if we have an algebra that looks like that has zero relations? So if I have an algebra that has got all kinds of zero relations from 1 to 2, from 2 to 3, there are zero relations, then they say, similar to the Bauer-Coelho-Simoes model, they say, those zero relations, they must occur as following consecutive edges in the same polygon. So that would look like so. So I would have 1, 2, 3 arcs in one polygon, and to those arcs in one polygon we would attach some. I need one more. We would attach some arrows, and each 2 consecutive arrows in the same polygon composed to 0. So this is pretty much the same model that we have seen before, and it generalizes all the triangulation model here. So they model the algebra by gluing together these two types of polygons. So they again consider dissections, cutting the surface into polygons of this or that type. They attach equivalent relation to it. In the same way, inside a polygon, we have zero relations. If you cross to the next polygon, you don't have zero relations. And they have a similar, they have basically the same model. Just this time around, what is the difference? What was the problem here? The problem here was when we pass through zero relations, then this does not correspond to an indecomposable module. Yeah. However, when you look for a model of the bounded derived category, the objects are complexes of projectives. So there would be projectives Pm -1 and so on, P2, P1. So there's projective objects, and there's some boundary maps dm up to d2, and each this is a complex, so each consecutive product di composed with di plus 1 is 0. That's just how really the derived category is defined as complexes between projective objects, between projective modules. And so it's kind of, it is a good thing if two consecutive arrows compose to 0. So if you have such a situation and you have a curve going from here to here, then you would model you would model an object in your category by you hit not a vertex. No, you hit a projective here and a projective there and a projective there, and if they compose to 0, this is very good. This is what you want. Yeah. So that works a lot better. So in this case, if you have a curve gamma going through here, this nicely describes you a complex of projectives going from here to here to here. This is perfect. Yeah. And if you have your curve going from here to here, then they would not compose to 0. Then you put them all together. Yeah, this is what Beckert and Merklin do in their homotopy strings. So their combinatorics of homotopy strings by Beckert and Merklin, their combinatorics of homotopy strings is that homotopy strings. These are sequences. Sigma is sigma 1, sigma 2, and so on. So these are strings. Sigma r, where each part of it, each sigma I, is a composition of direct arrows or their inverses. So these are all strings in the quiver. So either we compose direct strings or inverse strings, and whenever we compose two of them, sigma I composed with sigma I composed with sigma I plus 1 must be in the ideal. So must be 0. The composition must be 0. Okay, so this is kind of what we have. When we have a curve gamma going through here, then we say just, okay, this is a direct string. We put this all together. And when the curve gamma goes through here, then we have a composition of strings that compose to 0. So that combinatorics works just very well with the combinatorics of homotopy strings given by Beckert and Merklin. And that's what they use in their theorem, Oppe, Plamondo, Schroll, 2018, where they show that there's a bijection when we have a changed algebra, I mean, given by the surface S M, and the dissection of this given by a dissection of such a surface given by a dissection of such a surface, then there is a bijection. Then there's a bijection between homotopy strings and graded curves. Gamma f in this in the surface. And those homotopy strings, they correspond to indecomposable string objects in the bounded derived category. So you get that from Becker-Merklen's category classification, you get every object is a string or a band object. The strings are given by those homotopy strings, and they correspond bijectively to graded curves. In the derived category, you have some degree shift, so you would need to allow to shift the degree. You can do this, and you get really all kind of a geometric description of all objects that come from strings, and there's a corresponding thing for bands. Yeah, so you kind of get a nice description of all the objects in the bounded derived category. Okay. Okay. So this is basically everything that I wanted to present today. And before we open the discussion, I really would like to thank the organizers. I would like to thank Amit and the other organizers of that school for putting together the whole event. I think it was very successful. Many people stayed until the end, and I hope everybody really learned and benefited from that event. And we should also thank everybody who was helping around. Anoy, I think you were really busy the whole 3 weeks, so thank you very much.